all the pins are not used, all the address pins are not used for the interfacing or for decoding. We will see the first example. So the question is interface 2 kilobyte by 8, 2K by 8 byte of memory to 8085 microprocessor with memory address 8000 hex. So here the memory capacity is given 2 kilobyte, 2K by 8. Okay, so here 2 kilobyte of memory will give you the information about the number of address lines required, and into 8, so this 8 means number of data lines. Okay, so 2 kilobyte of memory capacity with 8 number of data lines, so 2K by 8. Okay, and the starting address is given 8000x. Okay, so we will go stepwise. So the step 1, so here we are going to calculate the number of address lines required to get 2 kilobyte of memory capacity. So we know the equation 2 raised to number of address lines equal to memory capacity. Therefore 2 raised to 11 will give you 2048 approximately 2 kilobyte of memory capacity. So here we are going to assume 11 number of address lines. So therefore total address lines required to get 2 kilobyte of memory capacity are 11. Okay, so A0 to A10 address lines of 8085 microprocessor we are going to use for memory interfacing. Okay, A0 to A10, that is 11 number of address lines. The second step, so here the address decoding table you have to draw. So first you have to draw the address decoding table like this. So you have to write the number of address lines, that is A0, A1, A2, A3, A4, A5 up to A15 you have to write as it is. Okay, then depending on the question you have to write the initial address. So in the question the memory address is given 8000. Okay, so this 8000 you have to write in the binary format. Okay, so to understand the number 8000, it is required to group these address pins in nibbles. So to understand the nibble wise address mapping, I have shown the address decoding table in various colors, blue color, green color, yellow color, like this. Okay, so you have to make the nibbles, that is A0 to A3, A4 to A7, A8 to A11, A12 to A15. So you have to group nibble wise. Okay, so first nibble consists of A12 to A15, the second nibble consists of A8 to A11, third nibble consists of A4 to A7, fourth nibble consists of A0 to A3. Okay, so after writing nibble 1 or grouping, at the right hand side you have to write memory address. Okay, 8000x. So in the binary format you have to write. So here 8000 means 1000 means 8. Okay, in the first nibble Here we are having 8. So here in the binary format 1000. Then in the remaining locations you have to write 00 because the address is given 8000x, that is 8000. So here everywhere you will get 000 means 0, 0000. Okay, so this is the initial address as per the question given. Then you have to find the final address. Then how to find the final address to get this 2 kilobyte of memory capacity? That is, the starting address is given 8000, but final address to get 2 kilobyte of memory capacity we don't know. Okay, so to find out the final address, we have already calculated number of address lines. That is, for 2 kilobyte we require 11 number of address lines. That is, we are going to use A0 to A10 address lines. So separate these A0 to A10 address lines first. Okay, so here A0, just draw line like this and up to A10. Okay, so group of A0 to A10 and group of A11 to A15. So here to get 2 kilobyte of memory capacity, we will interface or we will connect these A0 to A10 lines directly to memory IC. A0 to A10 address lines we will connect directly to memory IC, and remaining lines, that is A11 to A15. A11 to A15 address lines we will use to generate chip select signal either by using 3S2 decoder or by using logic gates. Clear? Okay, so after the separation you have to find out the final address. Okay, so by keeping A11 to A15 the bit pattern as it is, that is A11 to A15 1000, by keeping the bit pattern as it is, you have to write final address, that is A0 to A10, you have to write 1111 everywhere. So in this way you will get final address. Okay, again we will calculate the nibble wise. So the first nibble is 1000 means 8. The second nibble 0111 means 7. Third nibble 1111 means F. Fourth nibble 1111 means F. So the final address you will get 87FF. Final address you will get 87FFX. Okay, so you can cross check this final address 87FF. Either we are getting the 2 kilobyte of memory capacity or no. Just subtract this final address 87FF minus 8000, you will get 7FF. Okay, so and if you convert this 7FF to decimal, you will get definitely this 2048, that is 2 kilobyte of memory capacity. If you are getting something different memory capacity, some different memory capacity or memory capacity or memory size, so it indicates that the selected number of address lines are wrong. Okay, so here A0 to A10 we are going to connect directly to memory IC, and remaining address pins or address signals A11 to A15 we will use to generate CS bar signal or chip enable signal. Okay, so this is the total 2 kilobyte of memory space. Thus 87FF minus 8000, you will get 7FFX. So this 7FF, if you convert in decimal, you will get 2048, approximately 2 kilobyte of memory capacity. So after address mapping and subtracting the final memory address minus initial memory address, suppose you are getting different memory capacity. At that time it shows that the calculated number of address lines are wrong. So at that time again you have to cross check it. So suppose here you are getting different answer, definitely something has gone wrong in the calculation of address lines. Okay, so this is about the address decoding table. In the third step, we will see the generation of chip select signal or chip enable signal. This is active low signal. So there are two ways to generate chip select signal, that is by using logic gates or by using 3:8 decoder. So as we discussed, this particular chip enable signal is an active low input signal. Therefore we will use NAND gate because it will give active low output for all high inputs. Okay, so suppose the remaining address lines A11 to A15, if you connect to NAND gate, you will get active low. But in this case, A15 pin is active high. See here, A15 pin is active high and A11 to A14 are active low or 0. Okay, so as far as this NAND gate is concerned, for all high input, the NAND gate will give you the active low signal. Okay, so out of these address lines A11 to A15, A15 is already active high and A11 to A14 pins are active low or logic 0. Therefore it is required to connect the inverters or NOT gates in between NAND gate and inputs. Okay, so the A11 pin is connected as input to the NOT gate, and from this particular NOT gate you will get logic 1. In the same way, for A12 again we require one more NOT gate, for A13 also, and for A14 also we will connect the NOT gates. So these NOT gates will give you the logic 1 output. So input to this particular NAND gate, you will get all logic 1s. So as all logic 1s are available with the 4 input NAND gate, the NAND gate will give you the active low output signal. Okay, and this signal we are going to connect to the memory IC. So this is the generation of the chip enable, active low chip enable signal or chip select signal by using logic gate. You can use the basic gates, derived gates and universal gates to generate chip select signal. The second way to generate the chip enable signal by using 3:8 decoder. So in this case, the ABC input consists of A11, A12 and A13 input. Okay, that is the remaining address lines A11 to A15 we are going to use to interface to this particular 3:2 decoder to generate chip select signal. Okay, so A11 to A13 are connected to ABC input. Then decoder enable pins G1, G2A bar and G2B bar. So A15 pin is active high, that's why this A15 pin is directly connected to G1, because G1 is also active high input signal, enable signal, and G2A and G2B are active low signals. So here the G2A and G2B bar are shorted and connected to, or where we are going to connect to A14 pin. So as the bit pattern to this A11 to A13 is 0 0 0, so obviously the O0 bar, so O0 bar to O7 bar, these are the output pins of 3S2 decoder. So here A11 to A13 consists of 0 0 0, so you will get active low output signal from this O0 bar pin of 3S28 decoder. So O0 bar pin you have to connect to the chip select signal of memory IC. Okay, so we have 5 address lines A15 to A11 with binary bit pattern 1 0 0 0 0. So we will connect A11 to A13 to ABC input. Okay, so depending on the bit pattern, ABC inputs are 0 0 0, therefore O0 bar pin gets selected and connected to chip select of memory IC. A15 pin will be connected as it is to G1 because it is active high input enable pin, and A14 pin we will connect to G2A bar and G2B bar commonly by shorting because it is active low input enable pin. Now the final step, that is fourth step, that is the interfacing diagram. So here you have to draw the complete interfacing diagram by assuming the steps involved in the previous steps. So this is the complete interfacing diagram. So this is your 8085 microprocessor. Okay. So here you have to draw first the demultiplexing logic. So output from AD0 to AD7 you have to connect to 74373 latch. Okay, so this latch will give the A0 to A7 separate address lines, and you have to draw separate D0 to D7 data lines, and ALE pin of 8085 you have to connect to latch enable of this latch IC. So for 2 kilobyte of memory capacity we require A0 to A10 address lines. Okay, so out of A0 to A10, A0 to A7 lines are multiplexed. Okay, that's why this AD0 to AD7 you need to pass through this particular latch device, that is by using demultiplexing logic, and remaining lines are non-multiplexed, that is A8 to A15 lines are not multiplexed. Okay, or not mixed with any other signal. So remaining address line, that is A8 to A10, you have to connect directly as it is to memory IC, that is 2K by 8 memory IC. So here A8, A9 and A10 directly you have to connect to memory device or memory IC, and remaining address lines A11 to A15 we have considered to generate chip select signal. So this is the first interfacing diagram by using logic gate, that is address decoding using logic gates. So this is your NAND gate that we have discussed in previous step. A15 is as it is connected to NAND gate, and A11 to A14 consists of 4 NOT gates. Okay, and output of this NAND gate is connected to chip select signal, active low input signal. Okay, and read bar and write bar control signals of 8085 microprocessor you have to connect as it is to read bar and write bar of memory device. Now in this case the type of the memory is not mentioned, that is RAM or ROM kind of IC. So in case of ROM IC you have to connect only RD bar signal, that is read bar signal. Only writing is only reading is possible. Okay, so simply you have to connect single control signal, read bar signal, and if suppose the RAM kind of IC is there, so at that time you have to connect both control signals to RAM IC, that is read bar and write bar. Reading and writing both the operations are possible with RAM kind of ICs. Okay, so this is the complete interfacing diagram by using address decoding using logic gates, or chip enable signal by using logic gate. You can draw the interfacing diagram by assuming 3S2 decoder. So this is the complete interfacing diagram with 3S2 decoder IC. So this is your memory device. Okay, demultiplexing logic, AD0 to AD7 data bus, you have to connect to latch as an input, latch enable LE, latch enable you have to connect to ALE. From latch you will get separate address lines A0 to A7, and from this data bus D0 to D7 separate data bus. The non-multiplexed address lines you have to connect separately, A8 to A10 you have to connect separately to memory device. Read bar and write bar of microprocessor you have to connect to read bar and write bar. This is your 3S2 decoder to generate chip select signal. So A11, A12, A13 you have to connect to ABC input, A14 pin you have to connect to G2 A bar and G2 B bar, A15 pin you have to connect to G1 because it is active high. As the bit pattern with this ABC input is 0 0 0, you will get the output from this O0 bar, or the first pin of this particular 3S2 decoder gets selected. Just connect the O0 bar pin to chip select active low chip select pin of memory device. Okay, so this is the complete interfacing diagram with 3S2 decoder decoding logic. We will see one more interfacing example. Interface 1K by 8. Interface 1K by 8 byte of memory to 8085 using 1K by 4 memory chips with the memory address C400 hex. So in this question the total memory capacity is given 1K by 8, 1 kilobyte by 8. So here 1 kilobyte will give 1K will give you the number of address lines and 8 indicates number of data lines. But here they are telling that the using IC 1K by 4, using 1K by 4 you have to calculate 1K by 8 memory capacity. That is, to get 1K by 8 memory capacity you have to assume the 1K by 4 memory ICs. So first step, for 1K by 8 we will use 2 chips of 1K by 4. Why 2 chips? Because here 1K by 8 capacity is given using 1K by 4. Okay, so here data pins are required 8, but here with memory chips there are 4. Okay, so to get 8 data lines we require 2 memory ICs. So these 2 chips we will connect in parallelly and by dividing 8-bit data lines for 4-bit each. Okay, so we will split the data bus in two sections, D0 to D3 and D4 to D7. That is 4 bits. So for 1 kilobyte of memory capacity will require 10 address lines A0 to A9, which are connected commonly to both memory ICs, because the memory capacity is given 1 kilobyte, and to get 1 kilobyte we require 10 number of address lines. Okay, so here we will assume A0 to A9, 10 number of address lines. Okay, so here we require two memory ICs of capacity 1K by 4 and 1K by 4. So 1K means 10 number of address lines A0 to A9. Okay, so with first memory chip A0 to A9 to get 1 kilobyte of memory capacity. So 1K by 4. So this 4 indicates 4 number of data lines. Okay, so the data bus of 8085 we will divide in 2, that is D0 to D3 with first memory IC D0 to D3 4-bit, and with second memory IC D0 to D4 to D7. Sorry, here it must be D4 to D7. Okay, so D0 to D3 with first and D4 to D7 with second memory IC. Depending on the memory capacity, 1 kilobyte of memory capacity, same address lines, that is A0 to A9. So A0 to A9 we will connect parallelly to both memory ICs. Now we'll see the address decoding table. So you have to draw the decoding table like this: memory address A0 to A15 address lines. Then you have to group in nibble wise: first nibble, second nibble, third nibble and fourth nibble. Then you have to write the memory address, starting address. So in the question the memory address is given C400. So in the binary format you have to write, so C means 1100 means C, and 4 means 0100. Then 00 means, so in the third and fourth nibble you have to write 00000000 is the starting address. Then to find out the final address you have to separate the address lines. So to get 1 kilobyte of memory capacity we require 10 number of address lines. So A0 to A9 we will separate from A10 to A15. Okay, then by keeping the bit pattern in A10 to A15 as it is, you have to write the final, you have to calculate the final memory address. So A0 to A10 you have to write, everywhere you have to write 11111. Okay, so you will get the final address. So first nibble 1100 means C, the second nibble 0111 means 7, third nibble you will get F, and on fourth nibble again you will get F, that is C7 FFX. Okay, so here A0 to A9 address lines you have to connect to memory IC, and A10 to A15 address lines we are going to use to generate the chip select signal. So if you subtract the final address that is C7FF minus the initial address or given address C400, you will get 1023, approximately 1 kilobyte of memory capacity. That is C7FF minus C400, you will get 1 kilobyte of memory capacity. That is 3FF. If you convert that hex number to decimal, you will get 1 kilobyte of memory capacity. So as here we are getting 1023 or 1 kilobyte of memory capacity, that means the calculated number of address lines are correct one. If you are getting the wrong memory capacity, definitely the address line number calculation or count of address lines is wrong. Now here we will use the 3S2 decoder to generate chip select signal. So here we are having A10 to A15 address lines to generate chip select signal. So A10, A11 and A12 we will connect to ABC input to the 3S2 decoder. A13 pin we will connect to G2A bar and G2B bar because it is active low. A14 and A15 both are active high. That's why these two pins we will connect to G1, but instead of shorting we will connect one. We will give these two signals, that is A14 to A15 to two input AND gate, and output of the AND gate we will connect to G1. So in this way you have to connect the remaining address lines to generate chip select signal. So A10 to A12 to ABC input. So here the bit pattern is 001. So obviously the first pin of 3S2 decoder gets selected. So O1 bar pin you have to connect to chip select signal of memory IC. G2A bar and G2B bar directly we will connect to A13, and G1 pin you have to connect to two input AND gate, and A14, A15 is connected to two input AND gate, and output of this AND gate is connected to G1 because both the pins are active high. Final step. So here you have to draw the complete interfacing diagram. So this is your 8085 microprocessor. So first you have to draw the demultiplexing logic. So 74373 latch IC, latch enable signal you have to connect to ALA pin. Okay, AD0 to AD7 you have to connect to latch input. So latch will separate the A0 to A7 address lines and D0 to D7 data lines. So connect the A0 to A7 separated address lines to first and second memory IC. Also you have to connect D0 to D7, but what you have to do, as the memory interfacing question 1K by 4 memory chips are given. So here you have to divide D0 to D7 in 2. So first 1K by 4 memory IC with data pins D0 to D3, and second memory IC with data signals D4 to D7. Okay, so 4 signals to first and the remaining 4 to second memory IC. Okay, and A8 and A9 are non-multiplexed address lines, so you have to connect separately to both the ICs. So A8 A9 to the first memory IC and A8 A9 to the second memory IC. Then about the control signals, read bar and write bar. Read bar and write bar of memory IC, you have to connect to both memory IC, that is read bar and write bar input to these memory ICs. So in this question also the specific type of the memory is not given, that is the RAM, ROM kind of IC is not mentioned. That's why I have connected both the control signals to memory IC, read bar and write bar. So in case of ROM kind of IC, you have to connect only read bar, and in case of RAM kind of IC, you have to connect both read bar and write bar. And finally the chip select signal generation logic. Okay, A10 to A12 pins are connected to ABC input. A13 is connected to G2 A bar, G2 B bar. A14, 15 is connected to 2 input AND gate, and the output of the AND gate is connected to G1. Okay, and here the bit